So we start with the 7 feet. Like I said, we make it a fraction by putting it over 1. Our conversion factor is just a fraction we multiply by. And it has a value of 1, as I said. The numerator and denominator have the same value. But as I said, they may look quite different. For example, right here we have feet is what we have. And we're trying to get rid of feet. So to get rid of them, we're going to put feet on bottom here. And I know you don't like cross-canceling, but they cross-cancel. One's on top, one's on bottom. We're changing it into inches, so we're going to put inches on top. Now the relationship between feet and inches, 1 foot equals 12 inches. So 1 foot is 12 inches. That fraction right there has a value of 1 because the numerator and the denominator have the same value. It doesn't necessarily look like it, but it is. 12 inches and 1 foot are the same thing. They just look different. Now then, of course, like I said, the feet cancel out. We had to put the feet on bottom so they cancel out. That's how we knew where to put everything in that conversion factor. On bottom, it's 1 times 1 is 1. On top, 7 times 12 inches is 84 inches. 84 inches divided by 1 is just 84 inches. So that's how we know how to do that. I'm going to move down here, sticking with the standard measurements. So I have 48 ounces here that I'm starting out with. Again, I'll make that a fraction by putting it over 1. I need to do a conversion factor here. I'm getting rid of ounces, so I'm going to put them on bottom so that they will cancel out. And I'm going to pounds. So I now need to find a relationship between pounds and ounces. I look it up and I find that 1 pound equals 16 ounces. 1 pound is 16 ounces. 48 times 1 pound is 48 pounds. 1 times 16 is 16. So I have 48 pounds divided by 16. 48 divided by 16 is 3, so that's 3 pounds. Now the reason I wanted to jump to that one next is because in my math lab, they tend to not like to have numbers in the denominator. They like to have ones like this, where the denominator is just 1 followed by the unit. They don't like to have a number down there that we're going to have to divide by later. Now with pounds and ounces, there really isn't a good one that has, 1 ounce equals 0.0625 pounds or anything like that. So doing it for those is fine. When we get down here to 5 and 6, where we're converting from standard to metric or metric to standard, there are 2 different conversions given for each of those. So we'll look at those in just a minute.
Is it true we're the only country that doesn't use the metric?
The United States is the only industrialized country in the world that is not on the metric system right now.
Do you think it's harder?
The metric system, I think, is actually easier once you learn it because there's actually more sense to it. We had mentioned a little bit last class about, 1 gallon is approximately, I don't even use the straight equal sign because it's not exactly equal, but it's approximately equal to 231 cubic inches and so on. It's not a nice, neat little conversion. In the metric system, they plan this all out. Not only do we not have these weird conversions like 12 inches in a foot and 3 feet in a yard, it's all 10, 10, 10. Everything's 10 into the next unit. But they also planned it out. Like 1 milliliter is defined to be a cube that's 1 centimeter by 1 centimeter by 1 centimeter. So 1 milliliter is actually equal to 1 centimeter cubed, or 1 cubic centimeter. So you ever heard the term of cc? Well, cc stands for cubic centimeter. Yeah, 8 cc's of medicine, that's 8 milliliters or 8 cubic centimeters of medication. So 1 milliliter is equivalent to a cubic centimeter. 1 gram is defined to be the mass of 1 milliliter of water. So there's actually a relationship between the capacities and the masses and the lengths. things actually equal out instead of being like in the standard system. Capacity and lengths were never related to each other, so at one point they had to sit down and figure out, okay, well, how many cubic inches does it take to make a gallon? So that's why it doesn't fit nice and neatly. Many of those are approximate. As we mentioned on Monday, most of these units in the standard system have been adjusted through the years. Originally, there was no equivalency between inches and feet. They adjusted their lengths at some point to make 12 inches equal a foot and 3 feet equal a yard. But originally, there was no relationship. If you measured something in inches and I measured something in feet, there was no way to tell which one was longer or shorter because there was no conversion between them. So they adjusted them to make those conversions at some point. Now in the metric system, like we said, because it was planned, it didn't just evolve and then get forced together to create a system. In the metric system, every conversion is multiplying or dividing by 10, which means it's just a matter of moving the decimal point. Multiplying by 10 moves the decimal point one spot to the right. Dividing by 10 moves the decimal point one spot to the left. And the way we discussed doing that is we actually just use a chart. So meters is our main unit of length. Then it's decimeters, centimeters, millimeters, decameters, hectometers, and kilometers. And here, I want to convert 520 centimeters into meters. I am going from centimeters to meters. So from centimeters to meters is 2 spots to the left on my chart. So I'm moving 2 spots to the left. My decimal point moves 2 spots to the left. That's 5.2. So 520 centimeters is 5.2 meters. Yeah, that's only for, these are standard measurements that we use these dimensional analysis. We could use that here. I mean, I could do 520 centimeters over 1, and then put centimeters on bottom, meters on top. Say 1 meter is 100 centimeters. But that's kind of tedious when we can just move the decimal points. But again, that requires that you either have this chart in front of you or you have it memorized. The nice thing is that chart is the same no matter what metric unit you're working with. Like down here, kilograms and grams, well, I just replace this with a G. That's grams. This is decigrams, centigrams, milligrams, decagrams, hectograms, and kilograms. It's the same chart. And here I am going from kilograms to grams. Here's kilograms, there's grams. Going from kilograms to grams is 1, 2, 3 spots to the right. My decimal point moves 1, 2. I have to add a 0. 3 spots to the right, 720 grams. Any questions? Okay, so down here, my standard to metric conversions. To do standard to metric conversions is kind of a pain. You almost have to look up the conversion factor if you don't have it memorized. Here we've got 3.8 gallons. I'm going to put it over 1 to make it into a fraction. And I'm going to convert it into liters. So now I have to have gallons on bottom and liters on top. We must have, no, we don't must have. We can put whatever relationship between gallons and liters that we have, we can use. But my math lab uses the one where you have a 1 in the denominator. So the one, whatever relationship has 1 gallon in it is the one that we use. So in your textbook, you would find 2 different conversions. On that page 576, there should be one conversion somewhere that says 1 liter equals what, 0.2 something gallons? 0.264 gallons. That is not the one we want because it would be the one with the liters. We want the one that has 1 with the gallons. So there's one in there that says 1 gallon equals 3.79 liters, I believe, right? That's the one that we want to use here. 1 gallon 3.79 liters. Now, realistically, we could use either one. But both of these are rounded. I mean, some textbooks list this as 3.785 instead of 3.79. Both of those numbers are rounded off. And so that means that the answer is going to be rounded and it's going to be slightly off because of that rounding. So depending on which one we use, it might change the way our answer gets rounded. So using this one instead, it's still technically correct, but in my math lab, it's going to give us an answer that's slightly outside of the round off allowance. So if you did happen to use this one and my math lab marked it wrong, let me know and I'll change it. Because it's definitely not incorrect. It's just my math lab wants it done with ones in the denominator. So now it's going to be 3.8 times 3.79, which is 14.402. The gallons have canceled out, so the only units on top are liters. And on bottom, 1 times 1 is 1. So that's 14.402 liters. Centimeters into inches. So we're going to take 80 centimeters. We're going to put it over 1. And again, we're going to come over here. We're going to put centimeters on bottom so that they'll cancel out. Inches on top. Now we have the relationship that 1 inch equals 2.54 centimeters. Is that the one I want to use here? No, it's not. Because I want the 1 to be with the denominator, the centimeters. So I want to pick the conversion that has 1 with the centimeters. So on page 576, there should be one that says 1 centimeter equals 0.4 or 0.3 something inches. 394 inches. That's the one we want because it has 1 with the centimeters. It doesn't have to be, but my math lab wants it to be. To always have 1 on the bottom. So here, I'll show you with this problem here. I'm going to use this conversion factor for now, and then we'll come back and we'll use the other one. So here the centimeters cancel out. This is going to be 80 times 0.394. Yeah, 3152. That's going to be inches over 1, so it's just 31.52 inches. If I had used the other conversion factor, so I still have 80 centimeters over 1. It's still going to be centimeters on bottom and inches on top. But what if I used that 1 inch is 2.54 centimeters? The centimeters cancel out. 80 times 1 inch is 80 inches. 1 times 2.54 is 2.54. So I have 80 divided by 2.54. Yeah, 31.50. So you can see they're really the same. It's just slightly different round off.
So on test,
On a test, I'll accept either one.
just my math lab.
My math lab always wants you to use the one that has 1 in the denominator. And like I said, on my math lab, on a quiz, if you used this one and my math lab marked it wrong, let me know and I will change it because technically this is still correct. It's just not the way my math lab wants it done. But there's absolutely nothing wrong with that. Okay, so when we ended last class, we were starting to talk about units of area and units of volume. Your favorite? Try to contain your excitement. We had mentioned 1 square foot is defined to be a square that is 1 foot by 1 foot. Well, how many inches are in a foot? 12. So this is a square that is 12 inches by 12 inches. So the area of that is 12 inches times 12 inches, or 144 square inches, or inches squared. So 1 square foot is equivalent to 144 square inches. A lot of people make this mistake if they give them 4 square feet converted into square inches. They're used to looking at it and say, oh, 4 feet is 48 inches. That's it. It's not the case, though, because it's not feet and inches. It is square feet, square inches. So we take our 4 feet squared over 1. Square feet are going on bottom, square inches on top. 1 square foot is 144 square inches. Square feet cancel out. 4 times 144, 576. 1 times 1 is 1. So that is 576 square inches. Not so bad? Okay. What if we have 63 square feet and we want to go into square yards? Take my 63 square feet, put it over 1. Now my conversion factor here, square feet are going to be on the bottom and square yards are going to be on top. I just don't know what numbers to put in there yet. So let's come back over here and look at where did this 144 come from? Well, 1 foot equals how many inches? 12 inches. But this is not feet and inches. This is square feet and square inches. So I have to square those. What's 1 squared? 1. Feet squared, of course, is square feet or feet squared. What's 12 squared? 12 times 12 is 144. Inches squared is inches squared. Just like working with our variables in the last unit, or actually 2 units ago now. Same thing's going to happen over here. 1 yard equals how many feet? 3 feet. But we're not working with yards and feet here. We're working with square yards and square feet. So I'm going to square each of these. What's 1 squared? 1. A yard squared is just a square yard. Equals what's 3 squared? 9. Feet squared is just feet squared. So 1 square yard is equal to 9 square feet. If we think about that, that makes sense. If I have 1 yard by 1 yard, this is 3 feet by 3 feet. 3 times 3, 3 feet times 3 feet is 9 square feet. That's equal to 1 square yard. So that does work out. 1 square yard is 9 square feet. So here it's 1 square yard is 9 square feet. Yes, I know we have a number in the denominator that isn't a 1, but I don't really care. Square feet cancel out. 63 times 1 square yard is 63 square yards. 1 times 9 is 9. 63 divided by 9 makes 7 square yards. What do you think? Confusing? Not terrible though, right?
Not gonna throw variables in there.
No. But I am going to throw in, what's a cubic foot? Well, cubic foot is defined to be a cube that is 1 foot by 1 foot by 1 foot. Of course, that means it's going to be 12 inches by 12 inches by 12 inches. Well, 12 inches times 12 inches times 12 inches is 1,728 inches cubed, which is equal to 1 cubic foot. 1,728 is 12 to the 3rd power, 12 cubed. So we're dealing with cubic inches and cubic feet. We have to cube the conversion factor. So we have 5,184 cubic inches. I want to know how many cubic feet that is. So 5,184 cubic inches over 1. My conversion factor, what units has to go on bottom? Inches cubed. And on top, I'm going to cubic feet, so that goes on top. My relationship is 1 cubic foot is 1,728 cubic inches. So the cubic inches cancel out. 5,184 times 1 cubic foot is 5,184 cubic feet. Over 1 times 1728 is 1728. Then I divide. 5,184 divided by 1728 is 3 cubic feet. No. No. They will come out decimals. I'm just trying to make it easy on myself here in class. So, 567 cubic feet going into cubic yards. So 567 cubic feet goes over 1 to make it into a fraction. What unit goes on bottom? Cubic feet. What unit's going to go on top? Cubic yards, or yards cubed. Which one's bigger? A yard or a foot? Yard. So that's going to be my 1 here. How many cubic feet are in a cubic yard? Well, 1 yard is how many feet? 3. But I have to cube it. 1 cubed is still 1. A yard cubed is a yard cubed, or cubic yard. 3 cubed. 3 times 3 times 3 is 27. Good. And the foot cubed is still cubic foot. So this has to be 27 that goes down here. Cubic feet cancel. 567 times 1 cubic yard is 567 cubic yards. 1 times 27 is 27. I divide that out. 21. Not horrible? Still horrible? We look at metric units. So there's our chart. And remember, each time we moved a spot on this chart, it was either multiplying by 10 or dividing by 10. So move the decimal point 1 spot. So if I have 48,000 centimeters and I wanted to convert it into meters, going from centimeters to meters is 2 spots to the left. I move the decimal point 2 spots to the left. That's 480 meters. However, what if instead of being 48,000 centimeters, it was 48,000 centimeters squared, and I wanted to convert it into meters squared? Now, each spot on the chart is no longer multiplying or dividing by 10. It's 10 squared. What's 10 squared? 100. And when I multiply or divide by 100, it moves the decimal point 2 spots. So now each spot on the chart is 2 decimal places. So from centimeters to meters is still 2 spots to the left on the chart. You have to double it. The decimal point has to move 4. So 1, 2, 3, 4. That's 4.8 meters squared. I didn't think it was horrible. Now what if that is centimeters cubed going into meters cubed? Now each spot on the chart is multiplying or dividing by 10 cubed, which is 1,000. When you multiply or divide by 1,000, it moves the decimal point 3 spots. So now every spot on the chart is 3 decimal places. So centimeters to meters is 2 spots on the chart. I have to move the decimal point 6, 3 times as many. So 1, 2, 3, 4, 5. I have to add a 0, 6. That's 0.048 meters cubed. So what if I have 0.37 cubic centimeters going into cubic millimeters? Centimeters to millimeters is 1 spot to the right on the chart. I have to triple it. I have to move 3 because it's cubed. I have to add a 0, so it's 370. Or I might have 0.75 meters squared going into millimeters squared. From meters to millimeters is 1, 2, 3 spots to the right on the chart. So I double it because it's squared. Good. So I go 1, 2, 3, 4, 5, 6. I have to add those zeros. So the 750,000. Because it's squared, I had to double the number of places. When it was cubed, I had to triple the number of places. Not too bad? Where this comes to play most often is when we are dealing with compound units. For example, if I were to tell you that I am capable of throwing a baseball at the rate of 90 feet per second, would you believe me? No? Thanks. We'll see you again in the fall. Think about it. Is that fast? Well, we're used to seeing speeds expressed as not feet per second, but miles per hour. So let's change that into miles per hour. So 90 feet per second is 90 feet over 1 second. If you recall, when we talked about rates and ratios, this is what we call a unit rate. The fraction is hidden in the units, but it really is a fraction. It's 90 feet over 1 second is that rate. Now I have to change feet into miles, and I have to change seconds into hours. I'm going to get rid of the seconds first. Seconds are on bottom here, so to cancel them out, I had to put them on top. Now I don't have a direct relationship between seconds and hours, so I'm going to go minutes first. 1 minute is 60 seconds. So the seconds cancel out. Now I have feet per minute. I still need to get rid of minutes. I'll put minutes on top, and then I can go to hours. 1 hour is 60 minutes. So now the minutes cancel out, and I'm now in feet per hour. So the hours are good. That's what I want. I have to change those feet yet into miles. So feet are on top, so I'm going to put feet on bottom, converting to miles. 1 mile is 5,280 feet. So the feet have now canceled. Now I have miles on top and hours on bottom. That's what I want, miles per hour. So I have 90 times 60 times 60 is what, 324,000 miles. Over 1 times 1 times 1 times 5,280. It's 5,280 hours. If I divide that out, I get, what, 61.36 miles per hour. Now, do you believe me? No? I think if I warmed up, I could probably still do 60, 65.
Is it like
Major league pitchers pitch about 90. Yeah. Well, minimum's like 80, 85 for major league pitcher, but most of the good ones are pitching in the 90s.
So how do you know, is it just something you have to remember, or like, you just put 5,280?
Well, that's a good question. I had the feet were on top, so to get rid of it, I had to put feet on bottom, so they cancel out. I have to have one on top and one on bottom, so they cancel out. And then I'm changing it to miles, so I put miles up on the other spot. Then the relationship, I look up my relationship between miles and feet. I get 1 mile equals 5,280 feet. So I put the 1 with the mile and 5,280 with the feet. I remembered it, but you can look it up if you need to. I will never force you to do this without having the conversion charts. So we can convert with other units like that. We might have one, like a pressure that's listed as 7 ounces per square inch. What is that going to be in PSI or pound, or let's go PSF, pounds per square foot. So we list this as 7 ounces over 1 square inch. And now we have to change both again. I have to get rid of ounces and I have to get rid of square inches. Which one do you want to get rid of first? Ounces. Okay, ounces are on top here, so where does ounces have to go in my fraction here? On bottom. And I'm changing them to what? Pounds. So pounds go on top. My relationship between pounds and ounces? 1 pound is 16 ounces. So the ounces are gone. So right now I am in pounds per square inch. I want it pounds per square foot. So I'm going to get rid of the square inches. Where do I have to put square inches in this one? I have to put it on top. Because it was on bottom here, I need to put it on top. What goes below it? Feet squared, square feet. 1 square foot is, careful, they're squared now. 144, very good. Square inches are gone. I'm now in pounds per square foot, which is what I want. So 7 times 1 times 144 is 1,008 pounds. 1 times 16 times 1 is 16 square feet, which is 63 pounds per square foot. Typical floor load for a building, by the way. Floor load, if you're designing floors for a building. 60 to 65 pounds per square foot is your typical floor load. If these are metric units, it's actually a little bit simpler. Let's say you have something running 2.8 milligrams per liter, and I want to know what that is in grams per kiloliter. That's 2.8 milligrams over 1 liter. And I'm going to just convert each. Notice I'm not using conversion factors. I'm just putting them down because in the metric system, we just moved the decimal point. From milligrams to grams on my chart, there's 3 spots to the left. So I move my decimal point 3 spots to the left. So it's 0.0028 for my grams. From liters to kiloliters is also 3 spots to the left. So I move my decimal point 3 spots to the left. So that'll be 0.001 kiloliters. And now to finish my calculation, I just divide them out. 0.0028 divided by 0.001 is 2.8 grams per kiloliter. Well, you got grams, you got meters, you got liters, can all go in the center. Then this is deci, grams, decimeters, deciliters, centigrams, centimeters, centiliters, milligrams, millimeters, milliliters. This way it's decagrams, decameters, decaliters, hectometers, hectograms, hectoliters. I know I mixed those up. Kilograms, kilometers, kiloliters. It's all the same chart. It's all the same prefixes.
So if I just write down like centimeters, decimeters, centimeters, I can
Yep.
still, I don't have to.
You don't have to make a new chart, no. Because liters to kiloliters, it just goes from the main unit to the one as the kilo prefix. It's the same movements for each.
And that's where it's messed up with my math, they just have the one chart,
Yep.
and I just kind of find the kiloliters, and then I'm gonna put on here.
They have the meters, yeah.
Yeah.
What they have is they have like, I think theirs looks like this GML, and then it's deci, centi, something like that. Yeah. Same thing. Okay. Well, we actually only ended up finishing up our stuff from Monday. We didn't really get into our new stuff for today yet. So we'll finish that up tomorrow. What we're going to be talking about is angles. And angles, to understand angles, we must start from the very basics of geometry. The most basic concept in geometry is that thing right there. Looks like a dot. It's called a point. And a point is nothing more than a location. It has 0 dimensions. What is a dimension? A dimension is nothing more than a measurable direction, or a direction that you can move. If I sit on that point, I cannot move in any direction without moving off that point. Everything in geometry is created from that point. For example, if I take that point and I move it in a single direction, I have created a line segment. The length of that line segment is equal to the distance that it moved. So whatever distance we move that point, that is the length of that line segment. It now has 1 dimension because there is 1 measurable direction. Also, if I was on that segment, there's 1 direction I can move in, back and forth. A lot of people refer to that as a line, but remember, a line would actually keep going forever in both directions. And in real applications, it's not very practical to have a true line. So a lot of times when we actually say a line, what we are referring to is that line segment. Now then there's the next step would be to take that point and move it in a single direction, but keep going on forever in that direction. And that is called a ray. A ray still only has 1 dimension because it's only moved in 1 direction. Now let's look at naming these. If I were to name this, I'd put a letter next to that. That would be called point A, or often just A. Over here, if this is A and this is B, that would be labeled like this. You put a line segment above it, A and B. It must be labeled by its endpoints. If there is a third point, let's say there's point C somewhere in here, I don't use C to name that line segment at all. It has to be A and B. It has to be the endpoints. But down here on my ray, let's say this is point A. Here's point C and point B. When I name a ray, I use that symbol. I draw the little ray. The first letter must be the name of this end point, A, or the starting point, however you want to look at it. Technically, it's really the starting point. That's where the ray begins. The second letter can be any other letter on that ray. So I could name this ray AC, or I could name this ray AB. Either one of those works. Now, a ray is often used to represent a vector. We used vectors when we were doing negatives earlier. We had the number line. I don't know why all my lines are slanting like that today, but that's okay. And our vectors represented numbers. Like if we had 6 here, the vector started at 0 and went to 6. Or if we had -4, the vector started at 0, went to -4. Like that. These vectors can only go horizontally, so they can either go positive direction or negative direction. Our rays are vectors that can go in any direction. So that ray gets defined using kind of navigational coordinates is actually where it came from. This is the east direction, the north direction, west, and south. Well, when you're doing navigation, you start at 0 degrees here in the east, and you go around counterclockwise. So this would be 90 degrees, 180 degrees, 270 degrees, and then 360 degrees would be back at 0. So this ray here, I'd have to give you this angle. If I measure that out, that might be 13 degrees. So this ray is going in a 13-degree direction. If I create another ray, so let's say that's my ray, but I'm going to go back to the same starting point here. I'm going to create this ray going in a slightly different direction, moving that point in a slightly different direction. I've created a second ray. Well, two rays that share the same starting point is called an angle. And that common starting point is called a vertex. The original definition of an angle, or the measurement of an angle, came from this idea of a direction. Like I said, this first ray is going in the 13-degree direction. This second ray, if I measured it, might be going in the, let's say that's the 58-degree direction. The size of the angle was defined to be the difference in direction. 58 minus 13 is 45 degrees. That is a 45-degree angle. It's a difference in their directions. Throughout time, navigation has become less and less used by people. You know, once upon a time, the average person knew something about navigation. Now they don't anymore. So we've come to define those angles a little bit more sloppily. If I start in a single direction and I make a complete turn, how far have I gone? How many degrees? That's 360 degrees. So a complete turn is 360 degrees. If I start in a single direction and I turn, so I'm going back the opposite direction, how many degrees have I turned? 180. Where'd you get the 180? Half of the 360. Or if I'm going in a single direction and I turn, and I'm going like this, how many degrees is that? 90 degrees. How did I get that? Quarter of the 360 or half of the 180. So now what we do is we actually define angles as what fraction of a circle they are. If this is, let's say this ends up being 23 degrees. We say that that's 23 degrees because that's 23 360ths of a full turn. Does that make sense? That is it for today. We'll talk more tomorrow about angles. There is a quiz. No, the quiz is on the measurements and conversions. That is due Thursday at 11:59 p.m. There's a new homework that's going to be due Monday. Like I said, if you start the new homework, we haven't covered everything in it yet. We'll finish covering the rest of that tomorrow.